friends, welcome to Jitesh classes. Today our topic is fluid statics part 2. We are starting in this session, and part 1 I explained about density, specific gravity and pressure due to gravity, that is only Gauss pressure. Now today I will explain fluid pressure for atmospheric pressure, including with atmospheric pressure. And if we take for atmospheric pressure, if we take a glass, in a glass of water, and we need to find the net pressure at point A. Net pressure at point A. Atmospheric pressure, for everything, if we take vacuum, no atmospheric pressure is acting on it. Atmospheric pressure means an atmospheric pressure, external pressure will act on it. PATM from up in air, if we in this liquid from up, the air is acting an atmospheric pressure on the fluid in this container. So the net pressure at A, in Gauss pressure we learned that formula. Pressure at A is rho Hg, H rho G, and plus this ATM, PATM, atmospheric pressure. This is the net pressure at point A. Now, for atmospheric pressure, I will say some more depth. For atmospheric pressure, this is a glass of water. And density of the water is rho. We will take a point P, pressure P. At this point, we need to find the pressure at this height. We know that the pressure will be same at the same height. Means for here, for this range, the pressure will be same for this point, the points on the same height. So from here we will take, this is theta, and of height h. This is P dash. We will take P dash, this point. Okay, for this, if we need the pressure, we need the pressure here. So this will be L sin theta. We will take this as L, this length as L, and this will be L sin theta is equals to H. So we will take that height as usually as H. So the pressure at this point P is pressure at point P dash plus H rho Z. It means that similarly a pressure is acting from upward, from air, that one plus the height of the remaining part in the liquid. So if we take this as atmospheric pressure and this is out of the liquid, then the PATM is pressure acting at that point. So the PATM pressure at that point and PATM plus the height of that, and that form the H rho Z, that we will take this. Similarly we will get that pressure at any point A. In before case we took for atmospheric pressure at this point A, we need the pressure. So this is H, and PATM is acting here. So P at A is equals to pressure at point A. Net pressure at point A is equals to PATM plus H rho G. This is of height H. See, means by using this, means we will take in this case we will take a PATM pressure, atmospheric pressure is acting at this point, and this is out of the liquid. So for this point we are taking this H rho Z plus this height now. Similarly, if it is out of this, we will take the point at this level, and this will not be. Here PATM is acting, so this is of height h. At this point the pressure will be PATM plus H rho Z. Average pressure on the side walls. We will take a closed vessel no atmospheric pressure is acting on this, because the closed vessel, no air will act atmospheric pressure on that liquid. So we will take it as vacuum, and this is of a height, this liquid, this contains liquid, and that is of a height h, and density of this liquid is rho. We will take this bottom, the length of this that bottom side, we will take length as s, and this is the side of a container, the side of a container which is containing liquid. In that, the liquid will act some pressure on it. I'll explain. We will take, this is a vessel and it is containing water, then the water will apply some pressure on the sides of this wall. Means at the bottom, because of more height, the pressure will become more, and it will act, a huge pressure will be acted at this bottom. So here the pressure is less. Normally pressure will, the liquid will apply some pressure, and here some more, it will increase and it will increase, and high pressure will be applied by the liquid on the sides of the container, high pressure at the bottom. So we need the average pressure. If we need the average pressure, we will take that average pressure. For measuring the average pressure, we will take at this center, and this is a part of this total liquid, the part of the total area. So this area is dA, and force on this is, means totally average force is acting on the total liquid is acting more, the force on the sides of the container. This is a part of that whole container, no? So we will take dF, part of the force, that one, and dA is equals to this side, this length into we will take this one as a height x. Okay, this we know that s into dx. For this area, dA s, length s into dx is the area of this part, and dF is equals to, we will convert dF is equals to, F is equals to pressure into area. So this Px into dA, Px into dA, dF is equals to Px, x rho g, this is of height x, and this is density of the liquid is rho, and gravity is acting downwards, some gravity, because no air, but some gravity is acting downwards. So x rho g into s into dx. We got dA is equals to s dx. We substituted that value in this dA. So we'll integrate both sides. Now we will get, if we will integrate this one, we will get f0 to f, we will get f. And next, here we will take this constants s rho g. These are constants. In that value, constant values, we will bring that outside, s rho g, and derivative of x dx. By integrating from 0 to h, we will get f is equals to s rho g into h square by 2. Completed. Up to here? Clear up to here? Next, f. Now f is equals to s rho g into h square by 2. We know that s into bottom s into h is equals to area. Sh is equals to area. So sh by 2 into h rho g. F is equals to A by 2 into H rho G. So we need, this is average force acting at the middle of that point, and that is the part force. We took DF as the part force. Now we got F, so that is the average force acting on the side walls. So for pressure, what the for pressure P average pressure F by area, force by area. So force is A by 2 into H rho Z. We will substitute that here. A by 2 into H rho Z by A. Here, next step, A by 2A into H rho Z. A and A will get cancelled, and we will get H by 2 rho G. Average pressure on the side walls acting on the liquid is acting, and average pressure on the side walls is equals to H by 2 into rho Z. We got P average is equals to H by 2 into rho G. And this, in the sentence form, we can see that the average pressure on the side walls is equals to the average pressure, half of the average pressure at the bottom. See, if we take that same one, we will take, it is of height H, and at this bottom, the pressure at the bottom is P is equals to H rho G. So half of H rho G is the average pressure on the side walls. That's the concept of average pressure on the side walls. Force acting on a regular shaped vessel. It means that we will take a cylindrical vessel. Cylindrical. It is a regular shaped vessel. So the wall will it will stop some with a force, normal force. Means the liquid is acting a force, the wall is exerting a force by the liquid, and the wall will give the normal force. So these are the normal forces. Like this, normal forces will be like this. So this, because due to this is a cylindrical vessel, regular shaped, so this and this, these all will get cancelled. These all forces will get cancelled. In downward direction, weight of the liquid mg is acting in downward direction, and normal force to that. So these forces these all forces are being cancelled. So N1 is equals to mg. N1 is equals to mg. And difference is between these two, sigma n is equals to 0, because these all will be get cancelled. So no force is acting on it, no external force. No, so that is N1 is equals to mg due to symmetry. In previous one, I said force acting on a regular shaped vessel. So in that net force on the side walls is 0. Here random shaped vessel, because it is not a regular shape. It is not straight. These are curved this side. These are bended this side. So in this P at this point is 0. We will neglect atmospheric pressure because it's a closed vessel, and we will take here. We know that if this is of height h and rho g is acting downwards, this is density of the liquid is rho. So P at this point is h rho z. P at this point is h rho z. So now here we will take height is and normal force is acting here in this direction, like that. At the bottom the normal force will be greater. Here this is theta. If you take this as theta, that will be like that, and we will take similarly at this side we we will draw a free body diagram of water. In that, a liquid, free body diagram of a liquid containing in that vessel. See this is a free body diagram. In this, mg is acting in this direction, n1 is acting in this direction, and so at this point we know that pressure is P is equals to H rho Z. So force acting at this point is F is equals to pressure into area. So H rho Z into area. Here area is, we will take area S or A will take area A. F is equals to H rho Z into A. So F at here is equals to H rho Z into A. So this is N1. The force is N1. Normal is acting. F and those both are same. So we will take N1. N1 is equals to H rho Z into A. So N1 is acting in this direction, mg is acting in this direction. Now here means we will take here for finding that resultant, we will change the direction into this side. So this will be resultant. Like that, same here, this will be resultant. Similarly at this point also, this will be resultant, and here this will be resultant. This NV will be resultant. Like that many NV1, NV2 we can take like that. Like that many all complete, but these are the resultants. These are the resultants, no? Though for that all mixing by adding all those we'll take an NV in this direction. So now NV means the normal force acting by the wall. NV is equals to N walls, side walls of a random shaped vessel. See, NV plus N1 is equals to mg. We already got N1 is H rho Z into A. By substituting the value N1 in this here, NV is equals to mg minus H rho Z into A. We will transfer this to this side. The sign will become minus. So in this, when we take a vessel, in that normal forces are acting normal forces by the liquid, and normal force will be acted by the walls. So the resultant of these all normal forces will be in upward direction. So upward direction is the resultant direction of that forces, all the forces. By adding all those we will get NV as the resultant force acting upwards, resultant normal force, and this is NV from the bottom. N1 is the force from the bottom, normal force from the bottom. So we got already H rho Z into A is equals to N1. By substitute for getting NV, N walls, normal force acted by this on the side walls is equals to mg minus H rho Z into A. NV is equals to mg minus H rho Z into A. This is random force acting on the random shaped vessel, and I will say you another shape, like it will be like a beaker. force acting on the same random shaped vessel. It is also random shaped vessel, but it is inward, inclined inward, and this is like a vessel. Now here this is of height h, and density of the liquid in this is rho, and pressure at here P is equals to 0, and here P is equals to h rho z pressure. We got that N1 is equals to N1 in this direction and mg in this direction. N1 is equals to we got N1 is equals to h rho z into A. Here here it will act in this direction, like this. So means it will act in this direction, in outward. The normal force is acted in this direction. This theta. Okay, we will draw a free body diagram of liquid. In old one, that is inclined in this direction, so it is acting downwards. Now it is inclined upwards, it is inward inclined, so the normal force is acting upward, and inside, if we take it resultant inside, then it will act downward. Means if we take by viewing inside of the vessel, the normal force is acting downward in the point of view of inside. See, this is free body diagram. N1 mg, you know about that, and here force is acting in this direction. This is the resultant NV, and here NV1, here also at the same height it is acting. Resultant is NV1, like that. We'll take all the resultants. It is also similar to the last one. Outward inclined. It is also this one also is similar to that one, but some signs will change. Positive sign and negative sign will come here. NV1 by adding. So in this total resultant, by adding all those resultants of the points of that molecules of that, all adding all those, the resultant will be downwards. Total by adding all these NV1 NV2, those are adding those all, we will get that downwards, and we in downward direction. So because we know resultant in this direction, so here resultant will be in this direction. Normally it is acting this normal will be the resultant of the normal will be in this direction. So N1, see here NV plus mg is equals to N1. By substituting this value here in N1 is equals to h rho z into A minus mg. Similar to the last one, but here positive sign and negative sign is changing. This is the topic of this random shaped vessel. It is like a beaker which we will use in chemical reactions. So here, but I'll say once again that in this vessel, if we take this vessel in this direction, the normal force outward, it is acting this side, and if we take that inside inward, it will come like this. So the resultant of every molecule, the resultant will be downwards, NV. By adding NV1, NV2, like that many molecules, by adding those all resultant, we will get NV downwards. NV downwards. So that NV is equals to, see, NV and MG are in same direction. So NV plus MG is equals to N1. N1 is in opposite direction. So that's why is equals to N1. NV is equals to H rho Z. By substituting this value in N1 we will get H rho Z by into A minus Mg. That is the topic of force acting on the random shaped vessel. This is case 3. Thanks for watching my video. If you like my explanation, kindly like, share and subscribe to my channel. To get notifications of my channel, kindly subscribe. To get notifications, kindly subscribe and hit the bell icon.